We're going to start learning about equilibrium now. And equilibriums, of course, are very different kinds of reactions than what you've encountered. So in this first of, I think, three little presentations, this one is just about introduction. So some reactions go to completion because they occur readily. Those are the reactions you have encountered so far, which means that you see the yield arrow going forward and forward only. So those go to completion. You don't have to think about what's happening for reverse or if anything is happening for reverse. Some reactions will progress slowly and you can see the reverse reaction also happening, but you may not also. It doesn't have to. However, when equilibrium occurs, then both forward and reverse reactions are happening at the same rate. So when equilibrium occurs, which means forward and backward is happening, then you have to show this arrow. And this is called an equilibrium arrow, in which case you have half of the arrow pointing forward and half back. And you can have full-headed arrow also. However, you must have something going to the forward and something going to the reverse. And this is an equilibrium arrow. So for example, here are two reactions. Here is nitrogen and hydrogen forming ammonia. Everything is in gas state and everything is balanced out. So the forward reaction gives us ammonia. However, ammonia can also go reverse to decompose to give nitrogen and hydrogen. So you can go back and forth all the time. And then here also with methanol, you can have carbon monoxide plus hydrogen to give you methanol. On the other hand, methanol can also decompose to give carbon monoxide and hydrogen. So these two are both equilibrium reactions. How do you know which one is which? The only way you can tell is by arrows. Okay, so these arrows tell us that we have equilibrium. The straight yield arrow tells us that we have just a forward reaction. So then we can actually use the equilibrium reactions to calculate what's called the equilibrium constant. The equilibrium constant it's a very interesting thing because it helps us to tell whether the reaction is favored in the forward manner or in the reverse manner. So that would be the quantification of Kc. In order to calculate Kc, you need to have, of course, a reaction which should be balanced out completely. And then the equilibrium expression is given by this kind of an equation where you have the products over reactants. So CD, products over reactants, AB. What you also have in the Kc expression is the concentration of each of these products or reactants raised to their coefficients. So for example, C is raised to the coefficient of C and D is raised to the coefficient of D. If it's 1, it's 1. If it's 2, then you have to put 2 over here, so which means it's squared. So the concentrations, that's how you would take care of the concentrations. So that is how we calculate what is called the equilibrium constant, Kc. The value of Kc can give us a little bit of an idea, as I said, about the progress of the reaction, which we will calculate later on. So for example, how would you write the Kc expression for this kind of a reaction? Very simple, straightforward, right? So you look at the products and you look at the reactants and then you write the equation out. So here's the product, which is methanol, and then the reactants. Hydrogen is 2 over here, so you have to raise it to the power of 2. For carbon monoxide, it's only 1. So it's pretty straightforward kind of a Kc expression. Yeah, some of these calculations are actually not all that hard. So to calculate Kc with given concentrations, very simple, straightforward. One of the things about the equilibrium constant, the Kc that we talk about, and this is what is different about equilibrium and the normal reactions, is that if you remember when we did kinetics, is that we had initial concentrations and final concentrations and the rate of reaction changed as you progressed forward, and then by the time went on and on and on and there was no reactant left, the rate of reaction was very slow. Now this doesn't happen in equilibrium. Why? Because as the reaction is progressing forward, it's also progressing backward. All right, so which means that you have the concentrations of both reactants and products. So here in the equilibrium concentrations, which you will see in this table, you will see that both of them are present at any given time. So if both of them are present, by the time you calculate their equilibrium constant using the expression, so here in this case it would be NO2 squared divided by N2O4 concentration. So by the time you calculate the Kc constant for all of these different experiments, it comes out to be the same for all of them. And it is the same because the reaction is in equilibrium. So no matter at what time you take the concentrations, you will come out to have the same kind of Kc. Okay, or you can try the concentrations with different experiments with different concentrations. Your Kc will come out to be the same. So if the Kc is going to come out to be the same no matter what kind of concentrations you start with, then how do you know whether your reaction is progressing forward or not? Okay, and for that we have something which is called the reaction quotient. The reaction quotient is QC, and QC is called the value of the equilibrium constant expression under any conditions. And what this really indicates, okay, is the progress of the reaction. So which means that if you have a reaction going on like this, you can take out a little sample from the reaction vessel, because remember the reactants and products, they're all together usually, and then you can calculate their concentrations and then calculate the QC, and from there on then you can tell whether your reaction is progressing forward or backward or where is it. So for example, you have this reaction where you have carbon monoxide plus chlorine to give you COCl2. So the Kc expression for this is COCl2, which is the product over reactants. The QC calculation is exactly the same way. Okay, so that doesn't change at all. The only thing is that QC is something that is not at equilibrium, which is that it is happening at any time. So you can calculate the reaction quotient at any given time, whether it's initial or after 2 hours or after 4 hours, whatever it is. So that's when you calculate QC. Kc is calculated only at equilibrium. That's the thing, okay? Or at equilibrium, you will have certain concentrations of the reactants and products. Qc, on the other hand, is a different thing, okay? Because you may not have the reaction at equilibrium at Qc. So let's look at how Kc and Qc are related. So if Qc is more than Kc, if Qc is more than Kc, which means the reaction quotient is more, then the reverse reaction is favored. If the Qc is equal to Kc, if both of them are equal, then at that point you are at equilibrium. Well, your reaction is at equilibrium. And if Qc is less than Kc, then the forward reaction is favored, okay, which means that the reaction is going towards the product side. All right, so that is the general trend for comparing the Qc to Kc. And I'm very sorry, you have to remember this, okay? There is no other way. So if Qc is more than Kc, then the reverse reaction is happening. And if Qc is less than Kc, then the forward reaction is happening, which means that you're just starting to form the products, okay? It's just starting to happen. So which means that you'll have more products forming at that time, because remember, products is on the top, okay? So if Qc is less than Kc, it means that you have less amount of product, so Qc is less. So if you have less amount of product, your Qc is going to become a small number, which will be smaller than Kc then. Logically, that's what the thing is. If Qc is more than Kc, it means that you have a lot more of the product, and therefore it's a high number. So therefore the reaction is going to start moving reverse, okay? And so that's the logic behind the Qc and the Kc comparison. Now, in general, over here, these numbers, I would not really, it depends on the Kc that you get. But anyhow, if you look at an equation and you see that Kc is very large, okay, that would be considered like 100 or more. If Kc is small, then it is like 10 to the negative 2, okay? So if you think about what should my value of Kc be, is it, small or large or whatever, but it can range from, say 100 to even, 10 to negative 2, to negative 4, or it can be extremely large also, 10 to the power of 5, 6, so really large. Kc at 1 is going to be equilibrium for sure, because then it means you have both concentrations to be equal. Equilibrium constants for gases, which is called Kp. Now Kc is for concentrations, and concentrations are molarity. Molarity is moles per liter. Okay, so that is what Kc would be. However, Kp is slightly different, not exactly the way the calculation works, but some of it, okay, but the way you set it up is going to be pretty much the same, except in Kp you're working with the pressure of gases. In Kc you're working with concentration, which is moles per liter again, but in Kp you're working with pressure. So here is the Kc expression for this equation where everything is in gas condition. So CD over AB, normal, okay, very normal kind of an equation. Kp would be exactly the same, except now you're dealing with pressure. You still have the coefficients, okay, raised to the power over here. So that is still the same, all right? And then what you do is you use the gas law equation, which is PV is equal to nRT, and concentration, remember, is moles per liter, which is then N over V. Okay, so that's what concentration is. So which means that PA is equal to, this is the molarity, NA over VA RT. So this is for, say, reactant A. Okay, that's what it's for. So when you calculate Kp then for the products and the reactants, this is kind of what it's going to turn out to be. Okay, because then the concentration is still there, right? The concentration is Na over Va. That is what this is. Okay. Na over Va would go over here. Okay, this would be Nc over Vc. So which means that the moles of product over volume of product, all right, times RT. RT is going to be constant for all because RT is constant there. Everything is happening at the same temperature and R is the gas constant. So the only thing that is changing in the concentrations is of course the number of moles and then the volume. Okay, so that's how we can actually manipulate this law. Okay, just a little bit. So then what happens? Kp is equal to all of these concentrations, okay, which you have here, times RT, and then raised to the power of the CD minus A minus B. So CD, remember you have to raise everything to the power of C or D or A or B. So here you take out all your RTs, and then you have C and D on the top and A and B at the bottom. So remember with the exponents, if you're dividing, you have to subtract. So C plus D, and if you're multiplying, you have to add. So C plus D and then A plus B down here, which if you bring it up, then it becomes minus A minus B, okay? So this is the number of change of moles, okay, that's going on over here because these small A, B, C, Ds are the coefficients, okay, that you have here. So here, this expression right here, this is kind of the same as this. It's not very different, okay? The only thing we're doing now here with this and Kp is that we're multiplying it by RT. So then what happens? Okay, so here becomes Kp then with the CD concentration over AB concentrations, and then RT delta N. Okay, delta N is of course the change in the number of moles. Okay, so then Kp is equal to Kc, which is this value over here, and then RT delta N. Okay, so it becomes simplified. You don't have to look at this equation and then, you know, back off and say, oh my God, I have no idea what to do with this. Well, this is how it is simplified. So here delta N is moles of product minus the moles of the reactant. Okay, and moles of product because product is on the top and reactants at the bottom. And R is the gas constant. So it becomes an easy calculation to do. All right, so write the equilibrium constant, okay, or expression Kp for this reaction, which is all in gases. So if you were to write the Kp expression for this, you would do it exactly how you did for Kc, which means that you will have the products over reactants. The only thing is you would be using pressure instead of concentrations. So Kp is equal to the pressure of methane and water, which is the product, divided by pressure of carbon monoxide and pressure of hydrogen, and hydrogen is cubed because you have 3 of those. And then to calculate from Kc and to change it into the Kc, Kp is equal to Kc and then RT. And why is this minus 2? Because this is 1 plus 1 minus 1 and then 3 over here. Okay, and so that means 2 minus 4. So which means that this becomes minus 2. And minus 2 means that you have inversed and squared. That's what it is. Okay, and so Kp then becomes Kc over RT squared. And that is just a mathematical thing. It's not chemistry kind of a thing. It's more math that when you have -2, then it is inverse and then squared. So that's how you would calculate for Kp if you had to express for a reaction. So let's look at an example for the calculation also. Then the value of Kc at 227 degrees Celsius is 0.0952. For this reaction right here, we did this before also, we saw the methanol reaction. What is the Kp at this temperature? Okay, so again remember Kp is equal to Kc RT delta N. Kc is given to us, which is 0.0952. That's given to us. Temperature is also given to us, okay, 227, but you have to make sure you get it to Kelvin. Why? Because R is in kelvins, okay? So R, this is the normal gas constant that we know of. So R is 0.0821, you can use that also. And so T is 500 Kelvin, and then R is the gas constant, okay? And remember, this is where we are. Delta N, okay, delta N is going to be the product minus reactant. That's the number of moles, okay? So product is 3 and reactant is 1. So 3 minus 1, 2, okay? Which means that this number over here is going to be 2. So which means that Kp is equal to 0.0952 times R, which is 0.0821 times temperature, which is 500, and you put that in brackets, and then you square everything, okay? And once you square everything, this is the answer you should get. Try it out. Equilibrium expressions, a little bit more about these. There are two kinds of equilibria, homogeneous equilibrium and heterogeneous equilibrium. Homogeneous is where everything looks alike, reactants and products in the same phase. So whether everything is solid or whether everything is liquid, gases, aqueous, whatever it is. In heterogeneous, they are in different phases, okay? So which means you have some solid, some gas, some aqueous maybe. So what happens then for equilibrium expressions is that you don't count the solids. Solids are never considered to be part of equilibrium. Same goes for liquids. Okay, so solids and liquids are not part of the equilibrium expression. So for example, if you're looking at the decomposition of calcium carbonate into calcium oxide and carbon dioxide, the K expression, the Kc expression for this is just carbon dioxide because there's no other gas here, okay? So it's just carbon dioxide. Even if this was a liquid, you cannot have it as part of the equilibrium expression. So solids and liquids, okay, will not be part of the equilibrium expression, only gases and aqueous phases also, because they have concentrations as well. Okay, so here are some examples of writing some equilibrium expressions for heterogeneous equilibrium. So the first one, which is ammonium nitrate, to give you dinitrogen oxide and water. The other one is copper solid plus chlorine gas to give us copper chloride. So obviously you can see that the solids are not going to be part of the equilibrium expression. So for A, Kp is equal to, and remember we're doing Kp not Kc, so Kp here is just going to be the pressure of nitrogen and the pressure of water, okay, and that's, of course, you have to square that one. It's not going to be divided by any reactants because the reactant is a solid, so this is it. The Kp expression for the second equation, in the product you don't have anything, so the product remains 1. And in the reactants, you only have one gas, which is Cl2. So you just take the pressure of Cl2. So keep it simple, okay? Don't make it complicated. So no solids and liquids in Kp or Kc expressions. One of the neatest things about the equilibrium expressions is that you can manipulate them, like Hess's law, where you can actually take reverse reactions, inverse reactions, half them, double them, whatever you want to do, and then you can use the Kc or Kp to find out the new values of the Kc and Kp. So in Hess's law, you could figure out the new delta H or enthalpies of reactions. Here you can find out the new Kc or Kp of a reaction. So for example, let's look at the first reaction here. We have dinitrogen tetraoxide to give 2 moles of nitrogen dioxide. So when you write the K1 for it, which essentially is Kp, because here the pressures are given to you. So for Kp1, the pressure of nitrogen dioxide, which is squared because that's what the product is, and then of course the reactant, which is N2O4 here at the bottom. So for example, the K1 for this reaction is given to us 0.143. So at 25 degrees Celsius, I would ignore the temperature for now because all the temperatures are the same. Okay, and that's a key thing. Yes, it's important to have the same temperature because you can change equilibrium constant, but that is for later. So right now, let's just focus on the K1 here, which is 0.143. So now if you take a second reaction in which you're reversing everything, so for example, now you have 2NO2 to give N2O4 dinitrogen tetroxide, which means you reverse the reaction. So now what you'll do is you'll inverse the Kp. And so K2, the new Kp is going to be 1 over K1, the original K1 that you calculated. So because the K2 over here really is the product over reactant. And if you look at these two expressions, they are really just inverse of each other. So which means you can just take the Kc or Kp of this and you can inverse it and you can get the new value. All right. So you don't have to do all of these calculations. All you have to do is manipulate the Kc or Kp of the original equation. So the third equation here is half of the first one. So here you have half mole of dinitrogen tetroxide to give only 1 mole of nitrogen dioxide. So the K3 for this equation is going to be no squared over here because the 2 is not there anymore. It's just 1 mole. And then this is half. And so this is going to be halved also. The way it's halved is, of course, is to raise to the power of half, which means you're really square rooting everything. So then you take the square root of K1. So half of any equation and you take square root of the original equation. So then this is 0.143 and square root of that will give you this. So this is how you manipulate. This is very simple stuff where you double and you inverse and you half and all that. If you double, you have to square. If you were to add equations, okay, so if you were to add two equations, just hypothetically speaking, if you were to add equations number 1 and 4, if you were to add them, then you would multiply the Kp. So this equation, for example, the Kp is not given to us at any point where this is nitrogen dioxide to give us nitrogen monoxide and oxygen. So the Kp has to be given for this one. However, once the Kp is given for this one and you wanted to add these two equations up, just like Hess's law, then what you'll do is multiply the Kp's. Okay, so you don't add them up. Like in Hess's law, we were adding them up and all that, but not here. You won't multiply them. Okay, so here there's a slight difference from Hess's law. In Hess's law, you were adding and you were dividing by 2. Here, you're multiplying and you're square rooting, things like that. Okay, so it's just slightly different, but similar. So here are all the expressions that you would need. Here are hypothetical equations too, and then here are the Kc values for it. So exactly what we just did in the previous slide. Okay, it just goes over it again. So here is an equation, for example, a plus b to give 2c. So if you inverse the equation, you inverse the Kc. If you double the equation, then you square it. If you half the equation, you square root the Kc. Okay, and if you want to add two equations up, which means these two equations, to get rid of this c here, for example, then you would multiply the Kc1 and Kc2. Okay, so fairly easy things to do. I would keep this one handy in case you get confused, but this is how you would manipulate the Kc expressions. So here is an example of calculating and doing these manipulations for Kc and Kp. So here's a reaction, sulfur dioxide plus oxygen to give you sulfur trioxide. The Kp is given to us 2.5 times 10 to the power of 10 at 500 degrees Celsius. Again, remember the temperature doesn't matter right now so much. So compute the Kp for the following reaction. So here we have sulfur dioxide and half of oxygen and going to sulfur trioxide. So looking at these two equations, what you've done for A is that you have half the equation. So which means if you have half the equation, you're going to take the square root of Kp. Okay, over here, so 2.5, and you can square root that. I haven't done the calculations, you can do that yourself. Okay, but I'm just giving you the concept over here. In the next equation, look at oxygen. Okay, it's the best to look at oxygen because it has no moles over here, only 1 mole over here. So here you're multiplying the oxygen by 1.5. So if the whole equation is multiplied by 1.5, then you also have to take 1.5 of Kp. Okay, 1.5. You're going to raise it to the power of 1.5. Okay, so Kp, which means you have to cube it and then square root it. Okay, that's what you would do. Then the last equation is where you have inversed the reaction. So if you inverse the reaction, then you inverse the Kp, and then what else have we done? We've also halved it. Okay, so which means that we will also square root it. So if it's inversed and then square root it. So it's 1 over Kp and then half, okay, which is square root also. So anyhow, that is how you would do these kind of manipulations, all right? Very simple and straightforward to do. Just remember to square root the right things and inverse and all that. So from this little presentation, I would like you to be able to write the Kc expression for this, calculate reaction quotients, at least tell me if the reaction is going to go forward or backward looking at the reaction quotient if I give you comparisons. Calculate the Kp for gas reactions, again just the way that I gave you in the example, and then of course the manipulations of Kc and Kp. That would be it.